Quantum on the treadmill, the Dame du Radium. Before we move forward, let's do a checkpoint and go back in time a little bit. Most histories of quantum mechanics take us to Berlin in 1900 and introduce us to Max Planck. That is where the familiar story begins. Planck is struggling with blackbody radiation. The mathematics refuses to cooperate with classical physics, and he finally proposes that energy comes in discrete packets, quanta. That is a perfectly good place to start. But I want to rewind the clock a few years and travel from Berlin to Paris, because before Planck could begin rebuilding physics, someone had to help show that the old picture of matter was already falling apart. So let's spend a few minutes with Mrs. Curie, or as she would eventually become known, La Dame du Radium. Marie Curie is usually placed in the story of radioactivity, radium, and nuclear physics. I think she also belongs in the opening chapter of the quantum story. Not because she invented quantum mechanics, she did not, but because she helped reveal something deeply unsettling about the atom. The atom was not behaving the way classical physics said it should, and that matters. The story starts in 1896. Physics is already getting weird. Wilhelm Röntgen has discovered X rays. Suddenly, human beings can see the bones inside a living hand. The images are extraordinary. Newspapers publish them. Crowds gather around demonstrations. X rays become a scientific sensation. Around the same time, Henri Becquerel discovers another mysterious form of radiation. He finds that uranium can expose a photographic plate even without an external source of light. Becquerel has found something strange. Marie Curie realizes just how strange it might be. She begins measuring the effects systematically using an extremely sensitive electrometer developed by Pierre Curie and his brother. This is one of the important details in the story. Curie does not begin with a grand theory. She begins with measurement, sample after sample, material after material, different compounds at different conditions. And eventually she notices something remarkable. The radiation does not seem to depend on the chemical form of the uranium. You can alter the compound, you can expose it to different conditions. The radiation remains. That leads Marie Curie to a radical conclusion. In 1898, she argues that the mysterious radiation appears to be a property of the atom itself. That sentence does not sound shocking to us today. In 1898, it should have been. At the end of the 19th century, the atom is still widely imagined as the final building block of matter. The word itself comes from the Greek atomos, indivisible. You can combine atoms, you can separate molecules into atoms, you can rearrange atoms in chemical reactions, but when you reach the atom, you have reached the bottom. There is nothing inside it, and Marie Curie is effectively saying something is happening inside the atom. That is the first crack. Then comes an even more troubling question. What is causing the radiation? Heat does not seem to cause it. Light does not cause it. Electric fields do not cause it. Magnetic fields do not cause it. The atom appears to emit radiation spontaneously. Curie describes this spontaneity as an enigma and a source of profound astonishment. Think about that for a moment. The classical physics is built around a wonderfully reassuring picture of causality. Push something and it moves. Heat something and it expands. Apply a force and you get acceleration. Something happens because something else made it happen. The universe behaves like a gigantic machine. And now Marie Curie is looking at matter and saying, I can measure this energy coming out of the atom, but I cannot point to the external cause that made it happen. That is not quantum mechanics yet. But it is a warning. Something about the old mechanical picture of nature is incomplete. Curie keeps measuring. She discovers that some uranium-containing minerals are far more radioactive than the uranium alone should make them. There must be something else in there. Marie and Pierre Curie begin processing pitchblende, a uranium ore, looking for whatever is producing the additional radiation. And this is where I love the Curie story, because the beginnings of modern physics do not look very modern. There are no gleaming laboratories, no giant particle accelerators, no banks of computers. They are working in what amounts to a miserable shed. The floor is damp. Wind blows through the cracks. There are buckets, acids, iron rods, burners, and enormous quantities of ore. One visitor describes the place as something between a stable and a potato cellar. Marie Curie is doing backbreaking physical work, hauling buckets, boiling material, separating chemicals, measuring, repeating it again and again. Eventually, the Curies identify two new elements. The first is polonium, which Marie names after Poland, and the second is radium. And radium is astonishing. As they concentrate it, their samples begin to glow in the dark. Imagine seeing that for the first time, a material sitting quietly in a glass container, producing light and energy with no obvious external source. No flame, no battery, no electrical wire, no sunlight, it just glows. By 1902, after years of work, the Curies have produced roughly 1/10 of a gram of radium and measured its atomic weight. Now ask the obvious question: where is that energy coming from? To us, nuclear energy is familiar. To them, it is almost inconceivable. The atom was supposed to be inert and indivisible. Instead, it appears to contain an enormous amount of hidden energy. Then Ernest Rutherford enters the story. Rutherford proposes an even stranger idea that radioactive atoms are not merely giving off radiation, they are actually changing into other elements. This borders on heresy. For centuries, alchemists had claimed they could transform one element into another. Modern science was supposed to have left that nonsense behind. Now Rutherford is saying nature itself is performing transmutation. Marie Curie initially pushes back against parts of Rutherford's interpretation, but eventually the evidence becomes impossible to ignore. Atoms can change. Atoms have internal structure. Atoms can release enormous amounts of energy. Atoms are not the permanent, indivisible building blocks everyone thought they were. The basement has another basement, and this is where I want to reconnect the story to quantum mechanics, because now we can go back to Planck. Berlin, Planck is wrestling with another mystery involving matter and radiation. Classical physics cannot make the equations work, so he makes what he considers an almost desperate move. He proposes that energy is not exchanged continuously, it comes in discrete packets, quanta. A few years later, Einstein takes that idea seriously and uses it to explain the photoelectric effect. Rutherford develops the nuclear model of the atom. Bohr gives us quantized electron orbits. De Broglie gives matter a wavelength. Heisenberg gives us uncertainty. Schrödinger gives us the wave equation. Born gives us probability. And suddenly the universe looks very different from Newton's great mechanical machine. But before that new physics could be built, the confidence in the old physics had to weaken. That is where Marie Curie belongs. She didn't give us the equations of quantum mechanics. She gave us something that science often needs before a revolution can happen, an anomaly that refuses to go away. Nature was telling us that something was wrong with our picture of reality, and Curie listened. There is a wonderful scene from 1903 that captures the whole transition. Marie Curie has just completed her doctorate. She is celebrating with friends and colleagues in Paris. Pierre Curie is there. Ernest Rutherford is there. At some point, Marie and Pierre step outside into the darkness. Pierre reaches into his pocket and pulls out a small vial containing radium bromide. It glows. Their faces are illuminated by this strange substance. It must have looked almost magical. But there is another detail. Pierre's fingers are already burned and cracked from radiation exposure. They do not yet understand what that means. I love that image because it contains so much of the 20th century in one scene. Two people standing in the darkness holding a substance that seems to glow from within, and they do not fully understand where the energy is coming from. They do not yet understand what is happening inside the atom. They do not understand the biological danger. They certainly do not know that within a few decades, human beings will understand the nucleus well enough to build nuclear reactors and atomic weapons. They are simply looking at evidence that nature is stranger than the textbook said it should be. So, where did quantum mechanics begin? The standard answer is still a good one: Max Planck, Berlin. But I think there is another way to tell the story. Maybe the quantum revolution begins a little earlier, when scientists first realized that the atom itself is not what they thought it was. Maybe it begins with a woman in a leaking shed in Paris carefully measuring a mysterious radiation. Maybe it begins when Marie Curie has the audacity to suggest that this radiation is not simply coming from a chemical reaction, it is coming from the atom itself. Maybe quantum did not begin with an equation, maybe it began with an anomaly, with a faint glow in a glass vial. And with Dame du Radium forcing physics to confront a deeply uncomfortable possibility: what if our picture of reality is wrong? Planck would soon begin constructing a new one. But Marie Curie helped make the old one impossible to ignore.